So let's take the second part of the lecture for today, which is dealing with the mean absolute deviation models. And for short, we call them MAD models, so MAD, mean absolute deviation. And just to give you a brief idea of why I'm talking about this, there are essentially two reasons for that, why I'm talking about mean absolute deviation as an alternative to the Markovich model. So far, I've introduced you the Markovich model, which was Markovich linear or nonlinear? Nonlinear, right? So the first reason why I'm introducing the mean absolute deviation is that this is a linearization of the Markovich model. So when I'm talking about the mean absolute deviation in a few minutes, you will see how we can actually come up with a linear version of the Markovich model. Well, now this is maybe today is not that much of a big deal if you're talking about, especially when we have solvers like the CPLEX solver with the MIQCP, where you can have these quadratic terms in the Markovich model. At the same time, you can have binary variables like I just showed you, and still the solvers are pretty efficient. But back in the 1990s, where the computers were not nearly as strong as they are today, and the solvers were not nearly as good as they are today, then it was really a big deal if you could linearize a model. That was for practical reasons. That was extremely important. So that's kind of one reason. And even today, I would say, it's in some cases, if you can find the linear alternative to a nonlinear model which works, then again, the solvers still today are much more effective for solving linear models than nonlinear models, right? So that could be a good reason on its own, right? And it's an exercise how you linearize things. The second reason why I show this to you is that by going from the Markovich formulation to the mean absolute deviation formulation, then we need to use the notion of scenarios. Well, we do it in a gentle way today, so you will see it in its kind of natural setting. I'll give you an exercise afterwards where you have to look into just historical returns, and we just look at historical returns as possible future scenarios, and instead of looking into those historical returns and correlations, we use them as future scenarios, and then we will run the mean absolute deviation model. But that would kind of introduce you to the realm of scenario optimization, which is a topic I get back to later in the course. Like, I think that's in maybe about a month or a month and a half from now, where we will talk about the models like value at risk and conditional value at risk. So these are kind of some of the more advanced optimization models that you have to also work with extensively for the final project of the course. Right? And with that, let's have a look into what is the kind of the main difference between the input data which comes into the Markovich model, and how do we use the same input but in a different way in the mean absolute deviation model. So the first one that you're seeing here, the mean variance model is the one on the top. You have three assets, let's say, for this example, asset 1, 2, and 3. And then you have, for each asset, you have an expected return, right? mu1, mu2, mu3. So you already worked with that. And then you have this, by the way, is it a covariance matrix we're using in Markovich, or is it a correlation matrix? It's a covariance matrix, right? And correlation, what is the difference? What do you have in the diagonal of the correlation? The ones, right? So correlation essentially is a normalization of the covariance matrix, right? Where we just get ones. But we want actually to use, we don't want the ones. We want to know exactly what is the risk element. We want the variance. We want to know exactly what is the risk of the individual assets as well. So when you just normalize them, it seems like they're all equally risky, which is not the purpose of the Markovich model, obviously. So we need the covariance matrix. Right, so you have the covariance matrix there, the sigma 1, 1 to sigma 3, 3. That's the input of the mean variance model. And by the way, the first thing comes into the picture here. When we talk about the Markovich model, is there something, do we have the notion of time altogether? Do we talk about like investment horizon? No, you can see the model over here, right? Sum of x is equal 1, and then you are maximizing those two terms, right? There's no mention of time. You have expected return, you have a covariance matrix, that's all you have. Right? So what happens to time when you invest? When you think of it as something that if you want to do investments, would it be reasonable to think of an investment horizon? Yeah? So what happens then with investment horizon in the Markovich model? Is there any investment horizon in the Markovich model?
No, but if you want to implement it, you would add a new set, right? Is that how you...
Well, I mean, I'm going to challenge that you said no, there is not. I mean, there is, but it's not an obvious. It's not the one which is on the surface. There is an implicit horizon in the Markovich model. So there is, and what is the implicit horizon in the Markovich model? Yeah, but that, I mean, you can, what you are referring to is true, that obviously you can run the Markovich model several times. But what I'm saying, what is if you just run it once, even for that one time running the Markovich model, is there some hidden horizon in that one optimization on the Markovich model?
If you're talking about the mean and the covariance,
yeah?
They are calculated based on previous, previous history of the portfolio.
Some time step, right? So exactly. So if you're looking at these estimates, the estimates are estimated over some time steps, right? It could be days, it could be weeks or months or years, right? So the mu and the covariance matrix, the expected returns and the covariance matrix, they are based on some historical time series or time steps based on given a time length, and that length is the essentially the implicit time horizon in the Markovich model, right? So essentially, the numbers I gave you, I didn't tell you that what are those estimates, what time lengths they are over, but I think they're actually over a month. So these are monthly data that you get, and that essentially means that so far the Markovich model you've worked with the data you got, the underlying implicit horizon is 1 month, right? So once you run it once, then essentially you are optimizing as if you want to trade now and you want to keep your positions in a month. For that, it would be optimal. But then what you were referring to, that you can repeat that, obviously, then after a month, you can run it again and run it again. And that's true. That's one thing that you can do. So once you know that you have monthly estimates, then you can do reruns of 1 month. But then the problem with that is, and that's always the discussion which is going on, that do you want a dynamic model which looks into your true investment horizon? So let's say your true investment horizon was 10 years. So there are two things you can do, right? Either you can have 10-year estimates and then run your Markovich model once. Is that a good idea? Probably not, right? Or you can do like we did. You can look into monthly estimates. And then you can, as you said, you can suggest that to run this model 12 times each year until year 10, right? So that's you run this 120 times, right? Or, some would suggest maybe that, well, the best thing of them all to do is that to have a 10-year model, but you have a dynamic model. So in the model, you know that your horizon is 10-year, but then you allow, in the model, you allow to reallocate, let's say monthly or yearly or every second year or so. So that's an interesting discussion that we will get back to when we enter into the realm of stochastic programming. We wouldn't work so much with it, but we'll discuss it a bit further. But the very short kind of answer based on experience of many years of working both with these static models, like one-period models, and multi-period dynamic models, is that in many cases, actually, the static simple models done repeatedly work equally well or better than the dynamic model. So it's actually, sometimes simplicity does work. It's not optimal way of doing it in a theoretical point of view, but in practice, that's sometimes the best we can do, right? So that's something about horizon. But now we're talking explicitly about horizon in the Markovich model. If we move from the Markovich model to the mean absolute deviation model, now we have 3 assets, assets 1, 2, and 3, still the same assets. And let's look into 3 scenarios. And these 3 scenarios, let's assume that they are the last 3 months. And then you can look into the last maybe 100 months. You can extend it to any number of scenarios that way, right? So a very simple way of working with this is that we consider like historical months as future scenarios. So if you were assuming that what happened in the last 120 months, let's say, or in this case, the last 3 months, what's going to happen next month is going to be either of these 3 scenarios. You have a question?
Yeah, these 3 scenarios is for one asset or for all 3?
It's for all 3. So that brings me to the next point, which is then you say, well, scenario 1, in that you have a return for asset 1 at scenario 1, that's mu1, 1, and then a return for asset 2, scenario 1, that's mu2, 1, and then you have mu3, 1 for asset 3 at scenario 1, and the same thing for scenario 2 and 3. So you have 3 returns for the 3 assets at each of the scenarios. And then, to get us started, you in the exercise that we will work with later on, I'll give you some data. You're already given that data in the file called estimate.gdx, where you have several months. I think you can go like 10 years back or even more, and have monthly return data. And then you say, well, I have 120 monthly observations over the last 10 years. And then I assume that what's going to happen next month is I don't know what's going to happen, but let's play that it's going to be one of these 120 things that happened the last 120 months, right? So that would be like maybe a bit naive, but not the worst thing to do. You have many, many scenarios, and then you want to make a model and say, well, it's in average, we are going to see what we saw the last 10 years. That's probably very bad estimate in terms of average, but in terms of risk, maybe it's not that bad. Say, well, I mean, we have seen all kinds of things for the last 10 years. What's happening next month is going to be confined within what happened the last 10 years. Essentially, that would be the effect of using historical data directly. Very bad estimate for average return for next month. You can't really use it for that. But for risk management purposes, that's actually not a very bad estimator of risk, right? So this is the idea. So this is how you will use either historical data, or you could use other methods we'll get back to later for having some scenarios, and explicitly in each scenario you will look into what is the return of any given asset in that particular scenario. All right, and then your model would look something like this. So instead of the 2 terms of the Markovich model, so let's see what happens, because I have the 2 terms actually here. So we have the Markovich model here on the whiteboard, where the first term, which was your return, expected return, that's sum of I, mu I, xi. Now that one changes into a double sum, where the first one is over L for scenarios from 1 to capital S, which is number of scenarios you have. So you sum over all your scenarios, and then you find out what is the expected return across all the scenarios. So that's what the first term says, right? So instead of historical returns and historical averages, now you have returns over the scenarios, future scenarios that you have in your model, right? So PL, mu IL, XI, that's the expected returns of your portfolio across all the scenarios, right? The second term is the risk term. So what's happening there is you, instead of having XI, QIJ, XJ, now we have absolute deviation. That's where you get. So the first term is mean. It's exactly the same as before. Essentially, the expected return is there is no difference whatsoever. That's just a different way of representing the input to the model. Instead of just averaging them first and giving the average to that term, you're averaging them essentially in the model itself. But it's the second term which is the kind of the contribution in this way of formulating this model. So what you have there is that you have mu IL, so I'll just write it here. So you have this absolute signs here, just see what's going on, and then you have within them you have this sum, and it's important what this sum is summing over. It's summing over i's, which are the assets, right? So you're summing over assets from 1 to n, and then in the parentheses we say it's mu IL minus mu bar, which is the average return for asset I, multiplied by xi, which is how much you buy of that asset, right? And then outside that, you multiply by the weights of the scenarios PL, and then you sum over scenarios, which is 1 to S, right? So this is your new risk term, right? But what's happening here inside this absolute signs? Right? So what we have is, let's say for asset 1, and now we are for any given scenario. Let's say if I'm in scenario 1, for asset 1, I'm summing over, from asset 1 to all the assets. But let's say for asset 1, I have a case where I have a return for that asset at that scenario, which is greater than its average, right? Then for asset 2, the return could be less than its average. So let's say for asset I equal 1, let's say that is this number could be minus 0.02, and for I2 it could be plus 0.02. So what happens? These two cancel each other out, right? I'm summing over all the i's inside the sign, right? And then for I3, let's say this is plus 0.001, and that would be the contribution of these three. Let's say my portfolio is a combination of assets 1, 2, and 3, so the contribution to the risk term from those would be this little number, right? If alternative was that this was plus 0.02 and plus 0.02 here again, and plus 0.001, the contribution would be a bigger one, right? So the idea is essentially that this is, by putting this sum within these absolute deviations, we want to make sure that we get the diversification effect into play. Yeah?
There would be no difference. In the first case, it would be minus 0.001.
Right, because now, you see, so this in this case, this would be, I mean, you will get what I'm referring to is that, I mean, here, of course, the sum is 0.001, and here the total is 0.041, right? So what I'm saying that because they are both of them in the brackets, this is one scenario. Let's say this was assets 1, 2, and 3. And let's say this is now, the alternative was between assets 2 and 3, and let's say asset 6, right? So if you are minimizing risk, then because you want the effect that they cancel each other out, the algorithm will prefer to pick asset 1 rather than asset 6, because that's the one which cancels the effect of the other assets. So that's, in that sense, we want that effect that we get some assets which are uncorrelated with each other. That's the purpose of the model. That's why we put this sum inside the signs. But then what you're saying is that, let's say for one term, now let's go across in this sum, right? So say that was in scenario 1, and in scenario 2, that's what you're saying. So let's say the case still have the same three assets, 2 and 3. Now this becomes still, just to keep it simple, we say this is 0.01, and this is plus 0.01, and here is minus 0.001. So this is still a small number, but it's in negative now, right? But now we want the effect that whether it's a negative contribution or a positive contribution, we want both of them to contribute positively to the risk term. So we don't want this number, this plus 0.001, and this minus 0.1, for scenario 1 and 2 cancel each other out. Because the idea of the scenarios is that each of them, they have to contribute to the risk term. So that's why we put the absolute signs around here. So this would turn into a plus number, and this would turn into a plus number as well. So the contribution would be positive in both cases, right? So that's the idea of the mean absolute deviation model. Yeah?
Could you repeat once again what mu-IL stands for? It's the exact return for...
No, but mu-IL is the return of asset I at scenario L.
Okay.
The mu bar was the expected return for across all scenarios. Yeah?
How does that represent the risk? I don't quite get it.
Right, so it's an alternative to looking into the portfolio variance. So instead of looking into portfolio variance, we work with something we call portfolio absolute deviation. It's because this has got a this is a kind of mean. The model called this mean absolute deviation, right? So it's a deviation from a mean, right? Okay. So you have a mean deviation. So it can be shown that if your underlying asset is normally distributed, which is, well, we know is not the case in financial markets, but if that was the case, if you have with normally distributed returns, then you will say that the Markovich model, which is the mean variance model, will give exactly the same results as the mean absolute deviation model. So these two models, they are not the same, but they are equivalent under the normality kind of assumption. Yeah.
You also said that you wanted to make the problem linear.
Yeah.
And this is not linear still with the
No.
absolute values also. So and also maybe another related question is
Yeah.
that with the other is the first Markovich chain without like the plain
The plain vanilla Markovich. Yeah.
Running time wise, is it scalable, or like what would the motivation be to make a linear model?
Yeah.
If it's is it because of the long running time?
Yeah, well, I mean, to answer your first question, I'll get back to that in a minute, because you're completely right. So what you just said was that, well, we wanted to linearize the Markovich model, but now we have these absolute signs, and this is not linear. We know that these absolute signs, they are, well, they are linear, but they are non-continuous. And this is not much better. So if you're going to get into something which is linear but non-continuous, you have a function which has, looks something like that, right? So it doesn't get into the negative realm, right? Would be around some value, right? This is not very good. You can't really, the linear solvers are not very happy with this. But in a minute, I'm going to fix that one, so that's one thing. But your second question in terms of running times, normally what you have with, linear models run in general much faster. So if you have very large models, and especially when you add the 0, 1 variables to them, then in many cases you can, this could be several hundreds times faster to run it if you run on a linear model. So it could pay off to do that. But that said, again, there are, specifically when you're talking about the Markovich model, there are many people who have made some specific solvers to solve their Markovich model, which can be done efficiently. So today, probably that is less of an issue. But it's still the fact it's more efficient. But that was one of the reasons I was introducing it. The other was mostly just to introduce you to the notion of scenarios, and how you actually introduce you to your first scenario-based model that you later can extend to models like value at risk, conditional value at risk, where you can use the same notion, but it's a much broad notion. So when you talk about scenarios rather than models without scenarios, then it allows you to define risk more or less the way you like. And that's why I'll get back to the notion of scenario-based models. And this is the first of the kind. It's not really a model which we would in practice use for much, to be honest. Right? Right. And there's one note over here which you can have a look at. So essentially, if you notice, we have the PL, which is the weight for any given scenario L. It could be just equally weighted. So if you have 100 scenarios, then you can say, well, the weight of each scenario is 1 over 100, right? But you can also, like the formula that I'm showing you over here. So PL is equal 2 times L being the number of that scenario, divided by the cardinality, the total number of scenarios, multiplied by the total number of scenarios plus 1. If you use that formula, then sum of all the weights would still be 1. But what happens is that you're assigning more weight the closer you get to the time where you're executing a model, which is today, right? So that's an alternative way of defining weights. But let's have a look into your other question, that this is not really an LP. So when we have absolute deviation, you have the absolute signs, and you can try that in GAMS. You can start with just formulating this with ABS, and then that would be the absolute, and then you put it in your objective function, and the solver would crash. And it will tell you something in the effect of the model is non-differentiable, non-continuous, or something like that. Right. And but there's an easy fix for that, and that's the easy fix. So that was maybe another essentially thing which is nice about this formulation. So from an optimization point of view, it's interesting to know this trick, because you can use it any place where you want to work with mean absolute deviation or something to this effect. It hasn't got anything specifically to do with finance, but in general you can use this trick where you can change that term. So this term over here, what we didn't like was the signs, because they are non-differentiable, right? And they make your function non-continuous. But we can change that easily. So what we're doing is that we are taking this whole thing out and replacing it by this new variable that I called ADL, AD for absolute deviation, and we introduce this as a positive variable, or just as a variable. And then what you will see here is that you have AD once being greater than what is inside here, where you have mu IL minus mu I, and once again it's greater than the sum, where you just shift these two, so now you have mu bar I minus mu IL, right? So what that means is that would be the case that always one of those two terms would be negative, right? One of them would be negative, one would be exactly positive with the same numerical value, right? So if you have minus 2 in the one, you have plus 2, and vice versa. And by saying AD is greater than the greater of the two, right? So if you had minus 2 and 2, then AD would be greater or equal 2, right? So that is exactly the trick. That's exactly what the apps does. And you just want to get the number which is the bigger of the two. But notice here again, we are saying greater or equal. We are not saying equal. But why is it? Let's just write this example up. So I say if AD saying is greater or equal minus 2 and AD is greater or equal 2. So we say, all right, this one is binding, so AD is greater or equal 2. But then it could also be 3. Why is it that we can be sure that AD would be exactly 2 and not 3 or any bigger number?
Because you're attempting to maximize the negative product in the object functions, or choose the lowest one?
Yeah, great. You could follow that one? So that's again a case where objective function, together with the constraints, make sure that these inequalities would be binding. Because the argument was, because we are maximizing the negative of that term, so we are minimizing risk. And this is, remember, this number, whatever that represents, it's something to do with risk, right? So we want to have this as small as possible. So we want to minimize this. So it doesn't make sense if it was 3. Then it's an easy way to minimize it by bringing it back all the way to the border, right? By making this equation binding. So the objective function minimizing this figure makes sure that even though this one says greater or equal, at the optimal point it would be a binding inequality. Binding means it goes to its border, right? So in that way, that's using in an optimization setting, you can use that trick to do mean absolute deviation, just modeling the absolute signs without using a non-differentiable function in GAMS. And that is perfectly linear. You can use an LP solver to solve that. All right? So that was the first part of the trick, that was the first model in those. And those were the tricks how to do it. The second model in the series that I'm going of the mean absolute deviation is what we call a semi-MAD model, or semi-mean absolute deviation model. And the idea with that is already now we are playing with the idea behind Markovich, because let's see what Markovich essentially said. The Markovich says that if I have this density function, let's just to bring it to some extreme, right? So we're saying that we have, let's say we had 2 portfolios. One of them was like this. And then you have another one which looks like this. This is portfolio 1. This is portfolio 2, right? let's see. If this was the case, which one would, and you want to minimize risk, right? Which one would be chosen by the Markovich model?
First portfolio?
Yeah. Well, which one would you choose yourself?
Portfolio 2.
Yeah. Right. So this is kind of one of the problems with the Markovich model, right? So that we get back to this has got to do with the fact that we say that the portfolio variance is not a coherent risk measure. Coherent means something which makes sense, right? So this is an extreme case, but that kind of demonstrates one of the problems with the Markovich model, essentially, right? That it would prefer, in terms of risk, or that's, well, with the portfolio variance as a measure of risk, it prefers a smaller risk no matter if you have the case of a stochastic dominance. If you can show that there is a case that is more volatile, but even in the worst cases, you are going to do better than an alternative strategy. It doesn't differentiate between that, right? So that's one of the problems. There's another problem. So let's see if you had, there's this one case would be something like that. So I'll, this is one portfolio, and then I'll make another portfolio with maybe another color. So this is my portfolio 1. And then my portfolio 2 could be something to the effect of
What are the axes?
yeah, so this is return. These are returns, and these are probabilities. So these are density functions, right? So and portfolio 2 is the other one, right? So now portfolio 2 is obviously more volatile, right? It's a bigger variance, but we're looking at the return here. So again, if you were minimizing risk using Markovich, which portfolio would Markovich choose? Portfolio 1, because it's less risky in terms of because there's less variance. But what would you choose again?
Portfolio 2, since it's positive risk.
Right, it's a positive risk. You have a positive deviation from the average. That's the whole idea of the semi-mad model, right? So what we're saying here is, so these are, here I gave you kind of two reasons. I can come back with more later, but there are two reasons why the Markovich model is actually not that great an idea. In some cases, if you have the assumption of normality, and if we assume that we are working in a perfectly rational playground where we don't have cases like stochastic dominance and so on, then you can use it. But there are many things you have to make sure that they are in place before you can use the Markovich model. It's quite interesting as a starting point for your analysis, but you have to be careful about these things. And what we see here is that in the semi-mad model, we are trying to address this particular issue. So what we're doing is that we're saying, as you said, that what you really care about is not deviation to the right in this graph, is the deviation to the left. So this being your average expected return. You don't really care what happens to the right of that. You want it to, I mean, if it deviates too much from that, it's good. This means you are getting a higher return. Only if that meant also that it's going to be a risk on the left-hand side. That's going to be a problem, right? So what we really want to punish is the deviation to the left of the average. And that's what the idea of the semi-mad model is. So what we have there is that we are saying that this first term is still the same. The second term is now becoming, it's not absolute terms, but you're using the max function. So we are using the maximum of 0, and what you have in the parentheses has mu bar minus mu IL. So if the averages are greater than the returns, so what does it mean? These are the averages. So for the scenarios, we have some scenarios representing this density function, right? So the scenarios in which the average return is greater than the returns, those are the scenarios representing the left-hand side. For those values, we want to have a positive number. For everything else, so in the case that the number there is negative, so if the mu bar was smaller than mu IL, what would we get? We get some negative numbers, right? If this would be the cases where we're on the right of the average, right? So the scenarios to the right of average, they have greater returns than the average. So average minus those numbers would be negative. And then you have the max function, maximum of 0 and something negative is 0, right? So you're zeroing out all the values for the scenarios to the right of the average, greater than the average, and you are taking the values of the scenarios to the left of the average and contributing them to your risk, right? So if you would use that model, then in this case, you would use portfolio 2, not portfolio 1. Choose that, even because all the risk to the right-hand side, the model wouldn't care about that. And then if the return there was some weight on the return, the average return of that normally would be a bit higher. All right. So that's the idea with model 2. And then I actually get back here. I don't have because max also is not a linear function, but you can linearize that in a similar fashion. Can leave it as an exercise how you would do it. So, but I would tell you that there's one of these. If you just throw out one of those two inequalities, then you'll get the max function. Anybody wants to give it a shot? It's a 50-50 one. Which one shall I take out? And then we can examine it if it's right. So I'm suggesting that to get the max function up and running, you just have to throw either AD greater than the first term or the second term here. And remember what we wanted to do? We wanted to look at the scenarios where we want to punish those cases where the average was greater than the values of the scenarios. So which one do we want to keep? The second one, right? Because those are the cases we want. Those would be still positive, right? And the negative ones, we'll just throw them out. So that means if it's AD is a positive variable, it would just be 0. Right. Okay, that's all I had for today. And with that, you can carry on with the exercises maybe after a break of 10-15 minutes. So we start again, let's say 5 minutes to half. Unless you have a last minute question. I guess not.